Okay, let's take a look at one more example of finding a volume using the method of shells. And this one's going to be a tough one. It's not going to be apparent why it's tough right off the bat, but it's going to become a difficult problem. So let's work ourselves through it. Like usual though, we'll start with, a diagram, a picture of the equations. Okay, so the first one, y equals 2 times the square root of x minus 1. That's just a square root curve that starts at 1 and opens up and to the right. And all the 2 does is it just makes it a little taller than it usually would be. So it's just going to just ballpark look something like that. Okay, so that's y equals 2 times the square root. In fact, you don't know y yet, but I'm going to put that underneath because I'm going to need a little bit of room. So y equals 2 times the square root of x minus 1. And then the second equation is y equals x minus 1, which is just a straight line that hits the y-axis at 1 and has at negative 1 and has a slope of 1. So it's going to look roughly something like this. Let's see if I can draw it okay. So it's going to look roughly something like that. Okay, so the intersection you can see just is kind of shaped like a banana here. It's just this small region. Okay, now the rotation is going to be around the x-axis, so we're going to rotate it this way. So as we've done in the past, what we're going to do, or what I'll try to do, is I'll try to give you guys a mirror image down below. All right, so the mirror image would look something like that. I'll just kind of shade it in a little bit. And then we try to make it look three-dimensional, which is kind of on the tough side, but again, just give it the best try here. So I'd have curves, and then we'd have straight lines that hit there and there. And then to make it look three-dimensional, we'll try to do that. The axis of rotation, the x-axis would be right through the center like that. And so it would look roughly something like that. Okay, now what we want to do is we want to set up the integral that's going to allow us to find the volume. Now, need to put it back in everybody's head because the axis of rotation is the x-axis and we're using shells. That means that the integral will be in terms of the other variable, y. So everything has to be in terms of y. Okay? So that means we're going to be integrating. Okay, the innermost layer of paper towels is going to be here at 0, and then we're going to have layer, 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 out to this last one, which is going to be located where the two curves intersect. So what we're going to need to do is we're going to need to bring this point of intersection back to the y-axis and figure out exactly where that is. And how are we going to know where that is? How are we going to know what value that is? We need to figure out where those two equations are equal. That's where they're going to intersect. Okay? And they're going to intersect at what value? Well, the tricky part is that we want to figure out what y value they intersect at, but right now the equations are solved for y. We'd like to solve them for x, so what I could do, the one equation is very easy. Just move the negative 1 to the other side by addition. That one's easy. But the other one's a little bit tougher. What we'd have to do is divide both sides by 2. Then square both sides. And I need to move this box, so we need to square both sides. And then move the negative 1 to the other side by addition. Okay? So I've solved this equation for x, and I've solved this equation for x. And now I'm going to slide off the side of the screen here so that I can figure out where this value of y is going to be equal to this value of y. Okay? Alrighty. Now, how do you go about solving that equation? Well, normally we wouldn't do this, but it makes it a lot easier right off the bat. Would everyone agree that we could subtract the same value from both sides of the equation? So if I subtract 1 from both sides, the 1's cancel on both sides. Then what I'm going to do is multiply both sides of the equation by 4. So this side by 4, this side by 4, as long as you multiply both sides by the same thing, legal. And then because it turned into a second degree equation, I'm going to get 0 on one side. So I'm going to move the 4y to the left by subtraction, and then factor out what's common. And what this tells us then is when I set each of these equal to 0 and solve, the two curves are going to hit each other when y is equal to 0 and y is equal to 4. In looking back to our picture, I hope you can see that. When y is equal to 0, the two curves intersect. And then what the other one tells us is that it also intersects when y equals 4. So this value for y right here, let me choose my pencil, this value of y right there is 4. And so now I could back up to my integral and show that we're going to be integrating from 0 to 4. Okay? Now the three things then that we're going to integrate, like always when we use shells, the length, the width, and the height for every one of the layers of paper towels. Now the length is very easy. It's just from our formula. It's going to be 2 pi times y. The width is going to be the tough one. This is going to be the tough one. The height is very simple. That's just going to be the differential opposite of the axis of rotation, so dy. So what makes this one really, really tough is the width. What makes this one really, really tough is the width. Okay? And that's tough because when you look at the width of the layers, the width is going to be horizontal between the two curves. In all of our other examples that we've done, go ahead and look back. We've always been using either the x-axis or the y-axis as either a side or a bottom to one of our two-dimensional regions. Right here, we have a straight line on one side, and we have a curve on the other side. So the widths are going to be side-to-side measures in between two curves. Side-to-side, left and right, in between two curves. And so I actually would need you to think back to section 1. And when we had a similar situation to this when we were finding areas, not volumes, but areas, what we did was we used the phrase right minus left. And that's what we're going to have to do again to calculate the width of any one of the layers, is we're going to have to think in terms of what function is on the right minus what function is on the left. Okay? So let me go ahead and set that up in your integral. We're going to have to think of which function is on the right minus which function is on the left. Okay, so back to the picture. Which of the two curves is on the right for any one of the widths? Well, it's going to be the straight line. And the straight line equation looks like x equals y plus 1. Please notice I don't use the original because I need to make sure that everything is in terms of y's. So I have to use the second version where we've solved for x, right? So that it's in terms of y's. Okay? And then the second one, the second curve, the curve to the left, is going to be the, the radical curve. And when we solve that one, when we solve that for x, what we got as a result is y squared over 4 plus 1. And that then would be the complete setup for the volume. Okay, so much more difficult setup on this one than we had previously. Okay? Now, feel free and pause this, take a look around at anything I've done before, but I'm just going to go ahead and proceed to the rest of the calculation. So I'm going to factor out the 2 pi. Before I distribute the y into the width, I'm going to remove the parentheses. So I'll have y plus 1 minus y squared over 4 minus 1. And I'm doing that because the 1's then add up to 0, and so it makes the distributive property just a little bit easier. Now I only have to distribute y times y and y times negative y squared over 4. So I end up with y squared minus y to the third over 4 for my function. And at that point, now it's easy to integrate. Add 1, divide by the new. Add 1, divide by the new. Now please notice on the second term, we already had a 4 in the denominator, and then I had to add 1 to the exponent and divide by the new. So I started with a 4, and then I had to divide by another 4. So the 4 that I started with, and the 4 that I had to divide by then become the 16. Okay? And now comes the F tick. Again, I'll just multiply 2 pi times everything else. So start by replacing y with 4 everywhere. So 4 to the 3rd over 3 minus 4 to the 4th over 16 minus 0 to the 3rd over 3 minus 0 to the 4th over 16. And just a little bit more room to do the arithmetic, and we'll call it good. 64 thirds minus 16 is, let's see, 48, 16 thirds. 0 minus 0 is 0. And of course, 16 thirds minus 0 is 16 thirds. So when we multiply by 2 pi, we'd end up with 32 pi over 3 cubic units. And that would then be the volume of the 3-dimensional solid. Okay? A real tough one again, a real tough one because of the way we had to set up that width for all of the layers of paper towels. Okay? Alrighty, so now you should be set to try the rest of the problems in the assignment. Feel free to send me an email or a text, or not a text, a phone call. If you have any questions on this one, I'll try to help you out. Okay? Hope you're having a good day. Talk to you soon.